In the winter of 2022, Ukraine went dark, not from military defeat on the battlefield, not from the collapse of its armed forces, from missiles, aimed not at soldiers, but at substations. Between October 2022 and April 2023, documented strikes against Ukrainian electrical infrastructure occurred at a rate of more than 7 per week. The strikes did not target power plants first. They targeted substations, transmission lines, the hard-to-replace components that move electricity across a country. By April 2023, Ukraine's available power generation capacity had declined by 51%. The average Ukrainian household endured 5 cumulative weeks without electricity during the winter months alone. The objective was not the Ukrainian military. The objective was the lights. And every military planner paying attention understood exactly what that meant. Modern warfare does not need to destroy an army to paralyze a country. It needs to destroy the grid that the army depends on. The question that followed, and the question this video is built around, is a simple one. If electrical infrastructure is now a primary strategic target in modern warfare, how resilient is the American grid? The answer is not what most people expect. For most of history, military strategy was about armies, ships, and territory. Destroy the enemy's forces, occupy their ground, force a surrender. That model assumed the target was the military itself. Modern warfare has discovered a more efficient target. Everything a modern military needs to function runs on electricity. Communications networks require it. Logistics systems require it. Fuel distribution, hospital systems treating battlefield casualties, financial infrastructure funding the war effort, water treatment plants that keep populations functional require it. Destroy the army, and you have defeated the military. Destroy the grid, and you have paralyzed everything the military depends on and everything the civilian population depends on simultaneously. Ukraine was not just a military lesson, it was an engineering lesson. The Congressional Research Service confirmed that Russian strikes specifically focused on substations and hard-to-replace large power transformers, not power plants, with the apparent objective of isolating and destabilizing major sections of the grid, not destroying the system outright, degrading it, systematically, over time. The most dangerous weapon in modern warfare may not fire a single round. It may just know which node to hit first. But to understand which nodes matter and why, the grid itself needs to be understood first. Think of the American power grid as a circulatory system. Power plants are the heart. Transmission lines are the arteries. Substations are the branching points where current narrows and redirects towards cities, military bases, and hospitals. And large power transformers, the massive steel structures that convert high-voltage electricity into usable current at every major junction, are the valves. Without the valves, nothing flows. The United States operates 3 interconnected grids, the Eastern, the Western, and the Texas interconnection. Together, approximately 7,700 power plants, 160,000 miles of high-voltage transmission lines, and 55,000 substations move electricity across a continent in real time. The grid does not store electricity in meaningful quantities. It produces and consumes simultaneously, every second, 24 hours a day. Supply and demand are balanced in real time. When that balance breaks, even briefly, the consequences propagate faster than any human operator can contain. Large power transformers make that balance possible at scale. Each one weighs up to 400 tons. Each is custom engineered for its specific location in the system. More than 90% of all electricity consumed in the United States passes through a high voltage transformer at some point. They are not interchangeable. They cannot be ordered from a catalog. And they currently take between 2 and 4 years to manufacture and deliver. Russia understood this when attacking Ukraine. They did not aim for the heart. They aimed for the valves. The grid's designers understood this vulnerability. They built a standard specifically to prevent single-node failures from becoming catastrophic. But that standard has a ceiling, and modern military planning is built around finding it. The N1 reliability standard is the foundational design rule of the American grid. Think of it like a suspension bridge engineered to hold even when one cable snaps. The remaining cables absorb the load. Traffic keeps moving. The bridge survives. N1 means the grid must survive the failure of any single component without causing a widespread outage. In America in 2013, that standard was tested without warning. At 1:0 a.m. on April 16, unknown assailants opened fire on PG&E's Metcalf transmission substation near San Jose, California. 19 minutes. Approximately 100 high-caliber rifle rounds. 17 of 18 high-voltage transformers were damaged. $15 million in equipment was destroyed. Customers who lost power, 0. Grid operators rerouted electricity around the failed node before the cascade could begin. N1 held. The former chairman of the Federal Energy Regulatory Commission called the Metcalf attack the most significant incident of domestic terrorism involving the grid that has ever occurred. And it produced no blackout, because it was one node, uncoordinated, unplanned at the system level. Modern military planning is not built around attacking one node. To understand how a handful of targets can plunge a continent into darkness, you have to look at the invisible chain reaction that happens in milliseconds, a sequence so violent that it renders operators completely obsolete. Imagine a highway system at rush hour. Every lane is running at capacity. Close one lane. Traffic reroutes. The system absorbs it. Close 2 lanes simultaneously. Congestion builds. Close 5 at once. The system does not slow down. It stops. The power grid works exactly the same way, except the physics move in milliseconds, not minutes. When a transmission line trips, the electricity it was carrying reroutes instantly across every available parallel path, not by operator decision, by the laws of electrical circuits. Those parallel paths were not designed to carry the additional load. They heat. Resistance increases. Heat builds further. Protection circuits trip automatically. Now 2 lines are offline. The load reroutes again. 3 lines of electricity are moving through an infrastructure rated for 1. On August 14, 2003, a software bug silenced an alarm in a First Energy control room in Ohio. Operators did not know the Cascade was building. Between 4:10 p.m. and 4:13 p.m., 3 minutes, the sequence became irreversible. More than 400 transmission lines and 531 generating units shut down automatically. 55 million people across 8 states and 2 Canadian provinces lost power. $10 billion in economic damage. 1 alarm. Unread. The generators did not fail. They protected themselves by disconnecting from a grid that had become unsafe to be connected to. That cascade was accidental. No node was deliberately targeted. No transformer was physically destroyed. Recovery took between 2 hours and 4 days. Now consider the same physics, applied deliberately, to the right nodes. If you wanted to cripple the United States, why would you waste a single missile on a power plant? Why hit the heart when you can just cut the valves? What if America's greatest tactical vulnerability isn't hidden in a classified lab, but sits completely exposed, right behind a chain link fence? The grid has 7,700 power plants. Destroying them is extraordinarily difficult. They are large, dispersed, and many have independent security. Even destroying several simultaneously would not guarantee a national collapse. The grid would reroute. Remaining plants would increase output. N1 would hold, or partially hold. The actual bottleneck is the transformer, not the power source, the valve. Large power transformers are what determine whether the electricity generated ever reaches its destination. Each one is custom built for its specific location. There is no universal spare. There is no warehouse inventory for the critical high voltage units that sit at the most important nodes in the system. A single LPT weighs up to 400 tons and requires specialized transport. Roads are closed. Bridges are assessed for load capacity. The delivery alone takes weeks of planning. And before delivery comes manufacturing. According to a 2023 GAO report, LPT lead times have in some cases reached 4 years. The National Infrastructure Advisory Council's 2024 review named the transformer shortage a formal national reliability risk. Wood Mackenzie's 2025 data put average standard power transformer delivery at 128 weeks over 2.5 years. The Ukraine attacks specifically targeted substations and hard-to-replace transformers, not power plants. The CRS confirmed this. They targeted the valves, not the heart. The attack cost missiles. The recovery is measured in years of manufacturing lead time. Why has the Department of Defense spent billions ensuring its own survival while the civilian grid remains wide open? What do military planners know that the average American doesn't? And where exactly does their protection end and our danger begin? The Department of Defense is not waiting for the commercial grid to solve this. Every major military installation is being upgraded to operate an independent microgrid, a self-contained power generation system capable of disconnecting from the commercial grid entirely and sustaining operations indefinitely. Not a backup generator running on a fuel tank. A sovereign power system that owes nothing to 160,000 miles of exposed transmission infrastructure. The logic is direct. A military dependent on the commercial grid shares every vulnerability that the grid carries. A military that generates its own power removes that dependency entirely. The DoD solution works. At the scale of a base, the United States is not a base. The military has built its answer. The commercial grid has not. And the gap between those two realities comes down to a number most Americans have never heard of and would not believe if they had. not hundreds of targets, not dozens. A confidential internal FERC analysis, later confirmed by press reporting, concluded that destroying 9 specific interconnector substations and a single transformer manufacturer could bring the entire United States grid down for 18 months, possibly longer. A separate commission study found an even lower threshold: 4 substations in the eastern interconnection, 3 in the western, 2 in Texas. 9 points of failure in a system with 55,000 of them. The grid was engineered to survive any single failure. It was never engineered to survive 9 coordinated ones. Ukraine demonstrated what a sustained infrastructure campaign looks like against a modern grid. Rolling blackouts, cascading civilian impact, military logistics degraded. Population endurance was tested across an entire winter. Ukraine's grid survived because of Western support, emergency equipment transfers, and a defense industry mobilized to replace destroyed components. The American grid has no equivalent external support network, and the transformers that would need replacing take 4 years to build. The same decisions that built the most efficient power grid in human history also created a system where 9 precise decisions, not missiles, not armies, not a declaration of war, can produce consequences no emergency response can reverse in under 4 years. Grid resilience programs fund hardening projects. Strategic transformer reserves have been expanded. The military has built its independent power architecture. The work is real. The progress is real, and the gap between that progress and the scale of the vulnerability is also real. Modern military strategy has already moved beyond targeting armies. It targets the infrastructure that armies depend on. Infrastructure is no longer just infrastructure. It is a strategic battlefield.